right. Well, hi, everyone, and happy Friday to all of you. Friday, yes, it's Friday.
Friday.
Here, yes, indeed. We're going to talk about testing, in particular, a new feature of zio-test called Smart Assertions, because the old assertions were lacking in the intelligence department. I'm just kidding. These are, I don't know why they're called smart assertions. Well, we'll see why they're called smart assertions. The other assertions were quite smart, but perhaps required us users to be too smart sometimes. So really, the assertions are smarter such that we can be slower. Okay, hopefully that made some sense. We'll take a look at some code once I hit the correct button. All right, here's my screen. Here's
Your
everything.
voice is particularly soothing this morning.
Yes, I don't know why I'm talking like this. I was, yes. After we were working late, I had to leave suddenly for my lady was at karaoke night and summoned me. So I went to karaoke night and it was a good time. But I'm trying to, yes, speak soothingly because I did not speak soothingly at karaoke night. All right. Anywho, enough of that. Here we are in a file, Smart Assertion spec. I made this to sort of show off what we're going to be doing, what we're going to be talking about. So right now, I have an iTerm instance here with many ignored tests and a few suites that I sort of pre-prepared or just prepared. And we will be untoggling the ignored test aspect and looking at what's going on and then adding some other ones. But just to get us started and to ease back into consciousness for myself, we have this prepared for us. So let's see what we've got. So this, let's just take a look at the lines 15 through 18 here. Pretty miraculous. We have the normal, if you use zio-test, you have these nested suites, and the leaf nodes of this test tree, this beautiful test tree, are the tests themselves, whereas the branches are these suites so that you can organize them nicely, really organize them nicely. And here we have simple stuff, actually 3 test names, simple stuff. This is more just, I guess, int equality and then string equality, and then we have some list equality down here. It doesn't really matter much, but here I just have a value. It's not a great test. I'm not really testing any functionality, but one could imagine your fancy method calculation existing right here where I've just dropped in the number 0 and setting that to some result. And then I went to assert true. This is sort of the new method that exists in Zio 109 and onwards, which just takes as its argument list a boolean expression, potentially multiple boolean expressions, which will just be ANDed together. So each one will sort of form a different assertion. But we're just going to worry about one at a time for now. And here we're asking, and we're checking the assert that result is equal to 10. And while it has a 0 in it, it is still not 10, unfortunately. So if I uncomment or delete rather, that ignore test aspect, and I pop back to my terminal, we'll see that it ran over here. So let me make this a little larger and friendlier, potentially too large. And here it is. It's quite stunning, I'm sure, to everyone. It says that 0 was not equal to 10. We've all learned something. And then below, it actually shows the syntax of the code that you wrote inside of these parens in the assert true. And it will also highlight the exact sort of portion of the assertion, the syntax that caused this failure, where your expectation went awry. So here equals 10, that's what was not true. The result was great in and of itself. It was just a number. And then also below it, in this sort of faded terminal font style, it will show the path leading up to the left-hand side of the assertion. So we'll see if this had maybe some multiple branches. Let's instead say there was some person and they have an age, which is an int. And instead of just being a result, this was a person of age 123. And then we wanted to assert that their age was in fact, well, let's also give them a name string, and we'll call it Bobo. And let us take a look at what happens here. Okay, so it's basically the same thing as before, except the number is different. The syntax is different because we wrote different code inside of the parentheses. And then here we see that .age was 123 and result was person Bobo 123. So that's kind of what I mean by it shows the path, the evaluations, the partially evaluated path. Yes, the list of results as it walked from left to right, and as it was evaluated, and got more and more specific towards the inevitable car crash of the wrong assertion. So yeah, nothing too crazy yet. I mean, it's nice. I think it's slightly aesthetic looking. Oh, and you get a nice little link back to your code, so we can jump right back to the assertion that failed. That was there before, but now there's a little finger. So that's cool, little ASCII finger. Very stylish. Okay, and so on and so forth. I mean, it works with other types as well. One cool thing is that we've this is not quite out yet, but we have added some interesting diffing capabilities. This can be built on, certainly, but sort of as a first pass, here we expected list 1284, as we could see down here, we expected result to be 1284. However, result was 1234. Therefore, the only difference here was at index 2, where 8 became a 3. So this will sort of work in a nested manner if we had a list of lists, and so on and so forth. And actually, I could also show that we have this as well with people. So I could say person Boban and 100, and let's also make them 123 Bobanessa. And hopefully this works. And I haven't introduced a bug. Oh, it just says that they're not equal to each other. Okay. Oh, that's because, yes. That's because for that feature, we need zio-test.magnolia, which I don't think is incorporated here. So we'll look at that later as a bonus, because this involves using Magnolia to generate diffs of case classes. So for now, we're just going to get the not equal to, the standard not equal to, but we'll have a similar diff functionality for lists and case classes, and strings as well, if they're sufficiently different enough. Okay, but that's kind of the basic equality. So let's get to some slightly more interesting things. We have this prism suite, and let me actually just remove the equality suite for now, so we just see what we're dealing with. Okay, cool, it's gone. Okay, so let's start out with this. All right, let's first make it such that it will pass. So here we have an option event, and we're going to call option.get. And because, this kind of happens a lot in testing. You don't really care about making the most total, functional, beautiful code. You just need to dig into some object and get an assertion out of it. If it blows up, well, hooray, we were expecting it to. We just really care about the happy path in tests all the time. So it's kind of nice to use these partial functions in tests, and people do it. And the only problem is that if something does go wrong, it's a little hard to tell potentially what went wrong. So let's take a look here. Well, first it passed because that was indeed equal to 11. But let me make it equal to 10. And we'll see it looks very similar to what it did just previously, which is 11 was not equal to 10. Great. And we could see that it was an option was equal to sum 11, and .get got us the 11 out of that sum, and therefore it was not equal to 10. But what if this were instead none? So let's save this and go back. And whoa, okay, so now it says option was none. Well, that's a nice little domain-specific error. That's talking to us in the language that we understand. And it also is highlighted once again. So far, all the highlighting was sort of on the right-hand side, but now it's highlighted the actual bit that failed here, this sort of prism, if you will, this get, which was trying to rip the option apart and give us the sum case and didn't really care about the num case. However, this prism sort of blew up on us because our expectation that something was there, our implicit expectation by even using get, was not satisfied, unfortunately, because the option was none, and therefore option was none, and we get the nice little highlight there. So that's kind of nice, I think. The same thing for eithers as well. So, well, here I'm using the deprecated write.get syntax, and yes, 10 was not equal to 11, write 10. Sounds good, all checks out. But if this were instead a left of string, obviously we're sort of widening the type here, so we don't know. And now it's going to tell us that, yes, either was left. We did either option.write.get, and it sort of highlighted this whole thing. So it's kind of clever enough, and it is being clever. Like, this isn't necessarily going to generalize to all code. There's not some AI here. It's only going to sort of figure out what we tell it to figure out. But if anyone uses this, and I hope you do, and run into issues where you think it should be clever, but it's not clever, please yell at me, and I'll try to make it more clever for us. But in this case, write.get, instead of sort of telling us that option was none, it's going to sort of reinterpret this entire bit of code as well, you were trying to get the right out, but this either was in fact left such that it failed. And same will work with left.get. In fact, it will even work with toOption.get. So you think that would maybe do the option error. Oh, and never mind, it does. I think at some point I had that be extra clever for us, but perhaps that was a bad idea. Or I just, yeah, degradation. Okay, cool. Another sort of instance of this kind of prismatic access would be using the unsafe is instance of method. So let's try this. That obviously returns a Boolean, so we're sort of good to go. And down here, let me explain a little bit. We have this monster hierarchy of 3 monsters. It's a sealed trait. They all have different fields. Interesting. So here we have the mist, whose visibility index is 12.5. I think it could be double. And then we're asserting that it's an instance of feral shrimp. And of course, that could just fail yes or no, but it's nice to know that the mist was not an instance of feral shrimp. So we can get these sort of like nice error messages that have some colors on them. It's pretty. It might sort of help you understand what's going on a little bit faster than just this blew up. Good luck. Also, the highlighted code should help as well, give you some context there. And seeing obviously the partial values so you can see what it actually was. And likewise, as instance of works. And this is sort of like another one of these prismatic accessors where once you transform it into this thing, you might want to perform further accesses on it. And you would like it to, if it works, keep going. But if it fails, sort of short circuit. And likewise, it sort of gives you the same error message, except it will highlight that intermediate bit of syntax where that's what failed. It sadly was not a vampire. And so it blew up. But if it were a vampire and it were just not a bat, we're asserting that it is a bat, then it would fail for the normal reasons. So option.is instance of monster vampire is bat, that failed. Great, and this doesn't really have a special error message because it's totally, this is our method, we can't infer exactly what failed. But is bat failed, you can see it there. Hopefully that's helpful context. Okay, cool, so that's kind of this idea of prisms, things like that. This idea of reinterpreting normal standard Scala syntax to give us better error messages. So let's sort of keep on trucking and check out collections. So here's sort of a similar thing. Perhaps you could see this as the same way, but here I have a list and I'm trying to access the 6th element of that list, add 10 to it, and then assert that that is equal to 12. Now there is no 6th element of this list, so that would be a bummer usually. But in this case, it's going to give us another nice error message that tells us exactly what's going on. So invalid index 6 for list of size 2. So it'll let us know that this list is only 4 elements long if you didn't know, and you cannot access the 6th element of a 4-element list. And it'll show up the values and it'll highlight exactly the bit that failed. So cool. I think that's kind of, you're getting the hang of that. Here's one for exists. We're making sure that list exists. There exists a number greater than 10 inside of that list, which there doesn't. So it'll just say 0 elements satisfy the predicate. Okay, cool. Contains, obviously, that works on this and options and things like that. And it's just going to sort of just give us a nice human readable error, kind of similar as before, nothing too fancy there. For all is interesting. So here I have a list of those 4 numbers again, and I'm saying that for all should basically, modulo 2 equals 0, right? So we would expect that this should fail because, right, they're not all evenly divisible by 2. And when I save this guy, we get this error. Woo, 2 elements fail the predicate, list for all. 1 was not even, and 3 was not even. And it sort of shows what the, the underscore value was in this case. So it's possible to actually have these sort of nested assertions. Now, maybe this might get out of hand in certain cases if the list is gigantic, but it can be pretty cool because sometimes if you have these types of assertions, you'll just know that, okay, something blew up, I don't quite know why. This gives us the option to get even deeper into the failed assertions. And as you can see, modulo 2 is also sort of reinterpreted its failure. So this kind of composes in a nested way. For all was this sort of assertion type of thing, which then can have multiple nested assertions inside of it. And now that we've seen that, we can go back to this one, which is like, what if we wanted to assert that sort of like, let's say there exists a number greater than 2, right? Let's say that. and that's going to pass now, right? Because yes, there exists a number greater than 2. It's not even going to show up down here. But what if we say that there shouldn't exist a number greater than 2, right? Well, then it will do this for us and say 2 elements satisfy the predicate, and it renders it in this beautiful magenta. So when you see magenta, that's because the error message is actually going to be positive, and it's going to say, yeah, 3 was greater than 2, 4 was greater than 2. So it's not going to be negative. It's going to be a confirmation, but it failed nonetheless because it was negated. So despite succeeding, it still failed. And so that's sort of to distinguish visually for those who are not colorblind between magenta and red. I guess, it's hard to deal with that in ASCII. But besides that, you should get the idea. So yeah, 2 elements satisfy the predicate rather than 2 elements fail the predicate. So the for all exists duality. And likewise, I believe, we'll see what happens. Maybe I'll unearth the bug here. Yeah, list did not, okay, that just passed now, of course. Because yeah, that was not true. So yeah, that's kind of the basics of it. I did have this other example, so I guess I'll go through this as well and just kind of put this up here at the top level. So also, what if there are some real errors, right? So I have here a giant, this sleeping giant with the Fury index. I'll give it of 1,000, or rather 9,001. And then I would like to assert that taking the giant and poking it is equal to the number 10. So that would be, assert true, rather. So let's see what happens here. And I guess I've spoiled it. But yeah, so notice how it blew up. But it didn't blow up everything. It blew up, and it still highlighted the exact portion that blew up. And it gives us the stack trace of the error with normal links back to exactly what line the error occurred on and why, and the partial sort of evaluation up to the point where it blew up. And this is, as you notice, it's red now instead of the yellow of the normal sort of when it fails in a way that sort of we've handled, it will be yellow. So the option was none, the left was either, or the assertion was incorrect. But in this case, it was a total error that was unanticipated, probably, and not just this prism thing. So it explodes and gives you a nice error message. And that's kind of the basics of the syntax and how it works. So yeah, it can be nice for simple things or for nesting into large case classes where you just care about a particular value. And obviously you can sort of as well have these multiple assertions and OR them together just as before. So I can have well, I guess that's a bad example, but let's just make this an int and say 10. So I can say int should be less than 8, as well as int should be greater than 30. And then I can also say like int should be less than 8. Well, let's go one at a time here. So yes, this sort of turns into 2 different assertions, right? And that's basically the same as just doing and between them. This will also parse correctly, basically in the same exact way, actually, except you'll see the full syntax rather than it being broken up into 2 different sections. And likewise, if like one of these, you can have ORs as well, or int is equal to 10. So now this one should pass. And 10 was not greater than 30. Yeah, that's just this one. And so this one now passed. So yeah, that was there before, and it's still able to parse out intelligently what's going on. Yeah, and I think also that works with negation. I sure hope it does. Let's just take a look at this one. So it's a little tricky to parse mentally, but hopefully the code can do it. Yeah, so 10 was equal to 10, and that's why it failed. So that's magenta again, because this failed because that part was equal. So you don't really, yes, it can track it for you, the crazy Boolean algebra, which it already could, but it works with the assert true syntax as well. Anyway, I think that kind of gets us to the tour of the functionality itself. Are there any questions?
Yeah, so there's a question for you about for all is opaque. How come you know to continue with tail of list for more errors?
Yes. And that will sort of get us into the implementation here. Yeah, so this is clearly a macro, right? Normally, you cannot sort of just partially evaluate bit by bit, especially if, like, in the case where things blew up, right? Things exploded, but it didn't blow up the world. Normally, that would happen, and things would be very bad for us here. So we actually take what you write in here, and we regenerate it. We use the syntax, and we build something else out of it, which is going to be fun, I think, to explore. It was cool exercise, and it took a couple of iterations before we came up with something that was easy to write an algorithm to do, sort of, or an algorithm, a data structure, a functional domain. Actually, it's a bit of a DSL that sort of does this in a principled way that extends through large statements, and can also be used in that nested format in kind of a nice way. But yeah, basically the answer is we're not doing the for all directly. We are reinterpreting the code using a macro into something that we can inspect and run in our own way. Any other questions?
We have a question that people submit patents for 1% of this.
Can people submit?
No, sorry, a comment. A compliment to you that you've done 100 times the work that someone else might submit a patent for.
Oh, thank you. I'm not sure if my brain can't quite parse that compliment, but it feels monumentous and momentous. I don't know. It feels wonderful. It warms my heart. Thank you. Yeah. It was actually not so bad.
Yeah, it was fun.
Yeah. But yeah, we can talk about that. Are there any other ones, or should we get into the implementation?
I think people are excited to get into the implementation. It looks like one person's typing, so if they finish, I'll jump in on you. But otherwise, I think just go for it.
Oh yeah, and meanwhile, you can test this out today. This is there.
This is all live right now. So if you want to pull down your version of Zio and you want to start writing some tests, maybe you can see if you can break this, and we can give Kid a bug report to live code here.
Yeah, it definitely could use more of those special cases, like as we'll see in the implementation, sort of how it works. We kind of have to be explicit about what kind of code transformations we want to change into something nicer, to give nice error messages instead of just kind of a default fallback. Okay, so let's kind of talk about the process, I think, to getting here. Oh, is there another question?
No, so someone was just asking which version they get it on. I just typed it.
Okay. Yeah, like 109, I believe, the current.
Exactly.
Okay, so let's take a look first at the other assertion syntax, which is also great. Which would, well, I probably shouldn't do it with this one that blows up. Let me go back to my person example, actually. I'm going to steal just this one. Person. Okay. So one thing we could do here is the old syntax. So let's keep this, right? I'm checking that something's equal to something else. The other syntax was like this. So you put the result on the left-hand side of this 2-parameter list method called assert, and then you would use these assertions, which came in this assertion package, or still does come in this assertion package. Assertion, and yeah, I probably wouldn't just want to import equal to, but so yeah, I could say this is equal to, and then you put what it's expected. And this A is sort of constrained by the type on the left-hand side. So here I can put in, well, I can put in the same thing, and we should see that this is true, or I could write in, as I did previously, this thing. And it will sort of, if we go here, we'll see a similar error, right? It's a little different, the format, because yeah, we don't exactly have the syntax and highlighting and everything like that, but this is sort of it's the same thing essentially. It's that it does not satisfy this equal to assertion, and it's nested as well. So if this were instead an option of a person, and yeah, we add the type annotation there. So this is an option of a person. It is possible to do the same thing, but let me actually import all of assertion actually, because in this case, what we want to do is we want to say, all right, so the left-hand side is this option of something that we care about. And so we have also these prismatic helpers. So is some and is none. I can assert that it's none, and that satisfies it because this is an assertion that matches any option. This will be an assertion of any option. So basically, the type signature for assert, I should look at this real quick, takes an A, and then on the left-hand side, you need to have an assertion of an A. So if it's an option of A, then that is none assertion is an assertion of option anything. So it will satisfy the left-hand side. Okay, but if it's some, you might want to nest into that, right? There's more information. So is some is an assertion that takes a, oh, there's one that has no arguments, but there's one that has an argument. Yeah, so if you wanted to, you could just say it's some and I don't care. Is some anything? Or it could take a sub-assertion on the inside of the A. So the A in this case is whatever was inside of the option. So we have an option of a person. Now we make an assertion of a person. So it's is some equal to, and then we can do that same thing that we did before, the Bovanessa assertion, famous one. Yeah, and this will fail, and we'll sort of get a similar path here. It's a little different, but you can see that yes, person did not satisfy equal to, and then some person did not satisfy is some of equal to. Okay, so it's similar, and I mean, as you can see, like it's potentially in some simple cases, like it's definitely more powerful. You can really do anything. You can have many of these, and they can be prismatic, and you can combine them, and you can make nice partial ones. Like we have, like if there was a assert of a sort of a zio exit. So let's do.
Yeah, and I think for the folks in the audience here, I think one thing we're thinking about for zio2 is, should we basically just get rid of the old assertions? Because normally we like to have one way to do things. Of like, going to assert, like here's the way to assert. It's awesome, and we put all our thought into it, and this is just the way that solves all your problems. I think there are like, this is all like really great. I think there are a couple of areas where you kind of see why, like you potentially have like the more of the existing style of assertions. And so I think for anyone who is just looking at it or playing with it later, I think feedback's definitely appreciated of kind of as we look at some of these, like, do you feel good? Like we could just like get rid of the old assertions and you write all your assertions this way? Or does it feel like we kind of still like need to have both of them at some level?
Yeah. And to show off sort of something that might be a little more difficult, or the flexibility of the other one, right? Because you can sort of make any assertion, is that here, this is actually, if you didn't know, with the old style, it's a great way to test. If you want to make sure that sort of zio effect fails, for any reason, I guess, you can, zios have this run method on them. It's not a special test method, it's just run. And basically what it does is it sort of gets you the exit value. So it will return a zio that can't fail, because the failure and the success, everything becomes the full exit value becomes the result of that zio. So it's run sort of safely in a little sandbox and just get the result out, still within the zio context. So it's not actually running the zio effect and you can just get the value out and use it, but within a zio, because it gets back a zio of the exit value. And so if you call run, then you can take the exit, and then there are these assertions that are built directly for exit. So we can then have a sub assertion on the exit. So, is it a subtype of? So fails is subtype of, and then you can sort of, let's just say string. And yeah, that should pass, I believe, because I'm failing with the string here. And I think I then need to sort of have anything here, right? Yeah, so that also takes an argument list, because you can keep nesting down, because once you're in here, now you can have assertions on string. So that's sort of like you get increasingly nested. It's kind of like this optics syntax, sort of lensy. And that's very powerful because it's just this data structure, and you can run it in this principled manner. And so sort of what we were thinking, the first pass, you can kind of, if you squint, and let's maybe go back to this version, because currently there is no way of dealing with failure, right? Because we're sort of just rewriting standard Scala syntax. Potentially one way of doing this would be add to sort of like implicit methods, but not sure.
I mean, maybe even before you get to that, just like show just like the matching on it.
Oh yes, exactly.
Right, because I mean, like I think part of the thing that's nice about the assert true is like any problem you have, like you just solve the same way you would in like normal Scala code. So like if you've got this exit thing, like the exit's just a type and you just match on it and you like say whatever you want to say about it. So like, I mean, if you wanted to be negative, you can say, well, like it was kind of a little bit shorter the older way, but it's kind of the trade-off of like, well, you have to kind of know that like there's this like that you're supposed to run it, and then you're supposed to do this like assert fails, and the fails is the right name for it, and it's not some other name. Versus this is like, it's a little bit wordier, definitely, but it's also like you kind of don't have to know anything else to do that. So that's like one of the trade-offs like we're thinking about here, and we appreciate feedback from folks on.
I did notice that someone asked me why my intelligence.
Yeah.
I don't know if it doesn't always feel so fast to me, but it's doing all right today.
Yeah, it does. It feels very snappy. That's part of why I stick with VS Code. I feel like anytime I try, I'm like,
I don't know. Maybe I've got. I mean, it's a pretty fast computer. Let's see. What have I got here?
We're very snappy with it.
8 cores, 32 gigs of RAM. I don't know. It's maybe that's enough. I don't know why it's fast. Maybe definitely slower for other people. Yeah, the one thing I'm not to show off something. I'm curious what'll happen if because I haven't really. I'm not sure if I've tested this yet. So it's failed. Okay, so it gets a little uglier in this case. We'll see why maybe this is potentially more difficult to parse into something more intelligent. But I think that could be possible. It's not something I've worked at making very nice yet. I mean, it'll shows you that it failed, and this entire match statement failed. Basically, was the thing of it, because it's not being parsed in any special way. We're basically interpreting this whole thing as well, we'll see what we're interpreting this in a moment. Anywho, that's the old version, and you can do more things with it, and it's interesting. But in the simple case, comparing it to this, we can see that perhaps it's a little more verbose, and it's kind of nice just to write normal Scala methods. And yeah, it can be maybe a little clearer to read as well sometimes. Like, yeah, result get person, we know what that is saying, and now we have to sort of like back up, whatever. But if this were not rewritten with some magical macro, this would just not give us much information at all, and it could blow up at any time, and that would suck. But this, because it's this data structure, we have these series of values that are these assertions, we can run them later. We have there's a little mini interpreter, kind of like the Zio interpreter, not quite as complicated at all because it doesn't do concurrency. But it is running these assertions and nesting them together and building up something that can potentially handle failure, get the partial results as you go along, transform the error messages. Like, we have total control here around execution. So the first pass that we sort of thought about this is like, wait a second, we could probably sort of translate this in some principled way if you think about it, right? Like, if you move from right to left and you sort of see like, well, okay, here's the person, right? So that goes here. And then the next thing we did was equal to. So what if we take equal to and we just translate this into the corresponding assertion? And then when we did get, we can kind of do the same thing as well and translate that into an assertion, and so on and so forth, until sort of we get to the last bit. And then whatever thing is all the way to the left, we'll plop that in on the left-hand side. And we solved it. Wow, it sounds amazing. And we wrote that, and it basically worked. So the initial version of this was just translating it into this other style, which was cool, because then we got basically everything for free. We already did all the hard work. The only problem with that is that this is a sort of a very kind of particular kind of code that's very linear and has to be parsed a certain way. And it turns out that as well, the fact that you sort of want to end at some point, and like some bit all the way to the left is kind of the starting value, and then you sort of kind of like are folding over all of these assertions, is kind of difficult to figure out, to write a method that would sort of recursively move through this expression from right to left, but then sort of stop at some base element and then build this other thing in macro code. It was a little weird, because you have this special case, like everything is basically depending on this other result to sort of nest deeper and deeper inside of it. Whereas it sort of thinking it might be easier if everything were self-contained. I don't know if the monoid analogy makes sense here, but it's nice. So yes, this monoid is something that you can like a number, right? Like you can have a list of numbers.
You mean something that has an associative instance and identity, right?
Yes, an associative instance and identity. Yes. Now, if you have some associative data type, really is the cool thing, and some way of combining it together. you can just call like sum, right? So if you have a list of strings, maybe then you can map over it, turn them all into ints, and then sum them together, or fold left with, which is what sum does, or fold right with the plus operator. And why is that related at all? Well, if we can think of this expression as sort of like, if we could break it apart along some boundaries and translate each of them individually, and then smush them together later on into one assertion type thing, that would be easier, because this always needs to be parsed in the context of having something that it's going to get nested inside of eventually. So they are all interwoven together. You can't sort of do something in isolation like you can here, like mapping a list of strings. You can map each string individually into this other type, an int, and then crush them together in a principled, easy way. It was all entangled, and we had to be very sort of careful about it, and it got very ugly very quickly. And then it was hard to extend with that for all type of special case, and also if you do other non-standard things, like for instance, something you can do here is you can have a result where you get it, and then you can sort of say is equal to true, but then you can use result.get.age is less than 10, but then you can use this boolean again and do other stuff with it. Is not equal to true. I mean, that's kind of silly, right? You necessarily wouldn't want to do this, but there's no reason, like if we're going to be principled, we want to see every expression as a result of some value and not necessarily hard code it to this format, because otherwise people are going to do things as it gets more and more complicated, like the match statement, for instance, where it just does not really, you can't fold over it from right to left so neatly. It might branch out in certain interesting ways, and it could be a little weird. So what would be the way to think about this expression in a way that wasn't so much folding, like trying to turn it into this assertion syntax? Like if we could design it from scratch, what would that data type look like? And it kind of looks like the following. Well, let's first think, what could this like, what would the seams be? And I think a good place is sort of function application to break it apart, right? You have values, and then you have sort of functions on these values, right? .age, .get, and for each of these, knowing that we want for each of these to sort of store the result of .get, whatever that result of that is, and whether or not that function could possibly blow up. So sort of by looking at everything as a function, sort of might be interesting. But then what do you do when you get to these concrete values like 10 or maybe the starting one? Like that was the tricky one when translating into this version, because it was a special case. Like, how do we make the starting value not a special case? Well, we can have this type, and it's called an arrow. And you sort of have some inputs and you have some output. And if you have this, and we could basically represent this as a function, right, from A to B, essentially. And each of these little segments can get turned into an arrow of some kind. Result, you might think, well, what should the A be? Well, that could be just like if you're used to Z layers, that could be anything, right? There is no environmental sort of, it takes no input, essentially. It's a function that you can just pull out of thin air. If you've studied category theory in any way, and I guess I'm kind of getting there, I said monoid already, and now I'm saying arrow. Everything in category theory is kind of viewed at, there are no objects. I mean, there are objects, but there are no instances. Everything sort of, you deal with structures, you deal with observing properties of things by way of arrows, by way of sort of these functions. And if you just want to pluck a single property out of something, you more think of that as an arrow from sort of the categorical equivalent of this any type to that structure. So if you want to know the person's name, you can think of that as this arrow that's pointing in at the person's name. Anyway, that's silly, and I don't even understand that's terribly fully, but I was like, oh, this is kind of all connected, and I know that this is the concept. But really, I came to this conclusion just by sort of being much stupider about it, and just thinking like, well, I have this really concrete problem, which is that I want to view results just like everything else. I want to make everything the same. How do I factor that out? Well, if everything else is this kind of like partial function from the thing on the left, then this can just be a partial function from what's the result of, what's to the left of this result? Well, nothing is, but you can't really have a nothing type. So let's just have it like anything can start it. So you can kick it off with a unit value or really anything, because it's not even going to be used. It's just going to return you the result. And then what happens is there's a compose operator on this thing, which will take another arrow of B to C and get you the arrow of A to C. So it's basically it's function composition. That's kind of what arrows are. And this is sad because we didn't give it an interface. And so what this is going to turn into is result is going to be an arrow from anything to, what is it, an option of person, right? Option of person. So we'll have that. Get is going to be an arrow from option of person to just person, right? It's basically, get is this arrow that is going to take whatever's on the left-hand side and just unpack it. Obviously, it can fail. So actually, the actual syntax for arrow is a little more complicated. Basically, on this right-hand side, we have an either or an option. I forget exactly. We'll take a look at the real code. It's been a few weeks since I've actually poked around on that. But it's something that can fail, because this could blow up at any time. To the right of this is age, right, which will now take a person and get the int out of it. Then there's less than, which takes an int and returns a boolean. Okay, and if we compose all of these together from left to right, which we can, so kind of folding over this and just using this operator, which is way more simple and regular to do, because we can kind of do it in any context, rather than having some sort of like to do some crazy recursive method where you have to take the inner final result. That was really hard to do. This is just, okay, first we process everything into an arrow. You can kind of peel them off right to left in the macro code, which might sound complicated. And then just at the end, zip them all together with the compose operator. And then what you're going to get back is an arrow of any to boolean. And so what the actual implementation of this assert thing that it turns down to kind of requires, it can run any arrow of any to boolean. And because we are ensuring that in order to call this in Scalaland, we have to pass in an expression of boolean, we kind of are guaranteed, we can use the type safety of the, because this is going to basically, the Scala compiler is going to enforce that this is a valid syntax, right? If I, even though this is a macro, if I do something that's just an int, it's going to say, well, that's not a boolean, right? We need, well, it's going to get confused, but we need a boolean here. And so only a boolean expression will satisfy this. So we're guaranteed that once we process this expression as an abstract syntax tree in the macro, that we can sort of unpeel it from right to left, and we are always going to get an arrow from any to boolean, because for it to have parsed as a boolean, the right-hand side needs to be finally return us a boolean somehow, and the left-hand side is going to eventually terminate in some value, and so we can just wrap this in this kind of singleton succeed arrow that will just wrap anything up in an arrow. And that's kind of the structure with which we can build this large structure, sort of stealing every method, stashing this in here, potentially allowing for it to blow up in some way. And then finally, we have this large structured arrow structure, nested arrow structure, which we can then interpret in an interpreter and kind of like go through the cases. We can take a look at that. But I kind of just wanted to first give the conceptual overview and sort of what that is before we dive into the code, because obviously there's more noise in there. And I hope this kind of makes sense, as it's kind of a principled way of just peeling off from right to left. I should, by the way, mention that actually it's not just the greater than here, but it's kind of this, the 10 gets wound up in here as well, because the greater than 10 is what gets us a boolean. So 10 isn't, in this case, its own special arrow type. Yeah. Yes. Any questions on this stuff?
I think people are just loving it.
Okay, cool. Yeah, it was very cool to see like functional domain modeling and a little bit of category theory, half misunderstood from just watching Bartosz Maluski lectures on YouTube, was enough to sort of like actually improve macro writing code. Oh, and which doesn't mean the one point I do want to mention, because when I was doing the Zio magic stuff, I kind of realized that this is a cool pattern to follow, and I think it's pretty much what lots of people end up doing with macros. But Z-layer was super nice to work with. I loved it. It was so cool. It's what got me into Zio in the first place. I'm like, this is an amazing solution to dependency injection, like the most painful, boring part of application development. It's boilerplatey and error prone, and I hate that stuff. seemed to be solved so brilliantly. And it had one downside, which was layer construction could sometimes be a little annoying, but it was principled. It was lawful. It was this DSL, and it wasn't like, it was annoying because kind of it had to be. You needed to piece these together. You needed to tell it about the dependency graph, but it was type safe. There's only, the Scala 2 compiler isn't great at showing you these giant type errors sometimes. So okay, I was like, okay, the macro could do this. Like we have all the information at the type level. We can basically just do this sort of deterministically from that information, and it worked really nicely. And it was actually surprisingly easy to do because Z layer does everything. All I had to do in the macro was kind of like build a really simple like plus plus arrow arrow. It's like it's really a simple piece of code. It just got more complicated by like error messages and little nice edge cases and things like that for like error reporting and making sure things don't go in cycles. But the core of it like took me like literally a day, and it was super straightforward. And I was also learning macros at the time. But the sort of the revelation or whatever revelation-y thing makes it sound too important was that, oh, if you have a really principled like combinator library, start with that. Start with thinking about, if you're thinking about doing a macro, first think, well, what code would I want to rewrite this into that would let me accomplish whatever I'm setting out to do? So I wanted to be able to sort of like get the individual values, get really nice errors, catch partial methods, turn them into these prismatic assertions, catch errors that just blow up completely, compose arbitrary code and have ands and ors and all this. And then also the nested for all thing was kind of a stretch goal as well. And so instead of just sort of diving right into macros and be like, well, I'm just going to start translating stuff and make some crazy imperative thing that's just trying to reinterpret the world. Well, first, maybe we can make a composable primitive, this arrow type, basically is what it turned out to be, that could sort of solve that problem for the simple case, but then compose really nicely such that the macro doesn't really need to do much other than turn it into this other type. And it limits its complexity, and this nice composable DSL can solve your problem. So you can actually write this arrow code yourself manually. It just sucks because like, why would you do that? It's going to look horrible. Like that would never be a library that catches on, because there's like some arrow.succeed methods, so you can put the result in there, and then we can make a result.get. But obviously, we want the syntax.
We don't know any libraries with bad ergonomics that have lots of people using them. None of us have ever experienced that.
Yeah, so I mean, it's exactly, it's that same, it's sort of the same pattern as the Z layer sort of thing, which was that, okay, there's this great primitive. Obviously, Z layers wasn't nearly as painful as writing this would be, but there was some ergonomic gap, and you just need a thin layer of macros to translate that. So I recommend if you're thinking about macros, don't be overwhelmed by the macro part. Try to first figure out some kind of DSL that you could write that would be slightly annoying to write, but is principled and repeatable and composable. And then the macro can just really be some like sort of like thin translation from your syntax to this DSL. That's then going to do it nicely for you. And that's kind of what like the lens macros do as well, right? Like you have this nice lenses. There's a little problem with the boilerplate of writing the lenses. Therefore, macros come in. But the macros can be kind of simple actually because they're translating to this DSL that does most of the work. So yeah, that's a hot tip for you if you're thinking of writing a macro DSL. Start with actually thinking about the code that it would turn it into. Okay, but now let's actually look at the real arrow type. So let's go here, and there's this assert type. Okay, assert is just basically a wrapper around this arrow of any to boolean, which is the type that we know that we can run a test on, because basically we can kick it off with anything. We just pass a unit in, and then we can sort of start the ball rolling. We're eventually going to end with a Boolean or some kind of error along the way. But let's go to the actual arrow type. So here it is. As I mentioned, it's basically a function from A to B. You can think of it as. It has some other data, some metadata, right? We want to be able to print out, as you saw, like the highlighted bits. So for each of these arrows, along with each of these arrows, we also store its span, its range in the code in its context. So this will be from like character 14 to 18, such that we can highlight it if that happens to fail. If that bit of the arrow happens to fail, we can highlight it. And we also have some other metadata. Its location in the source file, its parents span, all these other things that it just needs for sort of highlighting some sort of, maybe can be simplified too. And just a bunch of helper methods. Here is the compose operator, which gives us back an and then And then also it sort of subsumes this, this Boolean algebra as well. So there's an and, or not. This could have been separated out probably, but it turns out it was just easier to make all this sort of, another lesson that I've learned from Zio is that instead of, okay, theoretically making everything super composable and breaking out different bits is a good idea. But sometimes if you only have one use case, why needlessly abstract? If like we are actually, this is not just a general purpose arrow, this is the special test arrow that we want to compose in Boolean algebraic ways, and may as well just hard code that, concretize and fuse them together. And that turned out to make it easier. I had a couple versions of each. Maybe I just was stupid and didn't do it right separately, but this seemed to work out pretty nicely. So down here are the cases of arrow. So it's a sealed trait, by the way. It's not quite a case class, but the case class I was showing before is kind of this one, and it's a little more complicated. So actually, what this is, what an arrow is, it's going to be a function from an either of throwable or A to a trace of B. And that's basically because it's theoretically possible for an arrow to the right to catch what's on the left. So something could blow up to the left, but then an arrow on the right might say, I don't care. That feature actually isn't in there yet. That was sort of like when I was thinking maybe there could be some implicit classes for like catching errors or like fails, like dot fails. If you want to assert that the left-hand side fails, then that would have to be able to sort of catch some upstream error. So I guess this might be unnecessary now, but every arrow has the opportunity to, if something to the left blew up, instead of just stopping there, you might have a throws assertion, which should be able to actually translate that back out into the error itself, which then you can have further assertions on. So that's why that bit's there. And then this trace type is kind of the path that it takes through. It kind of mirrors the structure of the arrow, but it has all of the results such that we can then use that to print a pretty representation at the end. We can look at that too. But are there any questions? I'll pause for a second.
I don't know questions. I mean, one thing I was just going to say there is, I think one of the nice things about this too is like, you've built this like really nice thing, but in a way it's like, it's just for you. Like the users like write these things and like, they just write Scala code. Like this doesn't even exist until you do your like, your macro, right? And you kind of look at the code and you like compile it down to this. And so if you go on later on and you decide, no, I don't need this, I want to change this, like there's not going to be like changing anyone's tests if you change this.
Yeah, no, this is totally not intended to be used by the users. I'm not sure if I can make it private just because the macro actually generates.
Sure. No, I'm just kind of saying.
Yeah. No, of course. That is a curiosity. I should probably hide it even more such that people can't even accidentally.
Maybe you can make the cases private, even though not the types. I'm not sure. I mean,
yeah, I'll have to explore that. That's a good point. Yeah, because I'll just need to keep arrow. Yeah, I could probably privatize these and finalize them. What am I doing here? This is terrible. I need way more. Private, final, lazy. Yes. Okay.
Explicit.
I don't know. Explicit, lazy. Just want to make some.
Not sure what's going to happen if we have to play. We have to have explicit vowels.
But yeah, as you can see, like these ands and ors, these all deal on arrows of any to Boolean. So that's kind of like our arrow version of just of a Boolean value. So it's kind of the Scala type system. There's the suspend thing, which is for it's a bit of an implementation detail, basically for the case where for like for alls and things like that. Not sure if that's an interesting thing to talk about, but because someone asked about that previously, let's kind of go over this for all thing. So for all, let's say we have some list and we call for all one on it, right? How should this be parsed? Well, the list itself can be this arrow from any to, let's say, a list of string, or let's start a list of int. And we're going to pipe this into some arrow that basically is going to take, well, a list of int. These always have to match up. Then to a Boolean, right? That's kind of what for all does. But inside of it, we kind of want to regain all the arrow capabilities. So for all is kind of a special one that expects an arrow to be passed to it. So we also take this thing and parse it into an arrow. However, there could be a binding, and you could actually do something really complicated where you say like 10, you could screw up the order, right? And in this case, this is sort of has to exist in some context. Like we want to parse this into an arrow where the left-hand side is going to basically be this any to int. We're parsing it right to left still into this arrow structure. But this I is magical. This I is meaningless to us here. We're sort of safe on the outer expression because it's going to get turned into code that if it's referencing some variable that's not there, it's already in scope, right? That's how you're able to call it in the first place. But if we're reparsing this whole lambda expression, then this I does not exist in global scope. It was bound explicitly here. So suspend, probably shouldn't call it that. I don't know what to call it. So it's kind of abstract here. Basically allows us to parse out the arrow, but add some context here. So it basically allows us to share this I for the entire insides, is kind of what that is going to do for us. Yeah, that's what that does. So we can then run this in a special way, and basically run each sub arrow separately with each input of the list, and then collect the results and nest that in some special way. So that's kind of, it's totally run at a different time, and it's not using the list for all. It's using a reimplementation that deals with arrows that, I mean, has the same behavior. It just gives nicer error messages and things like that. Okay, that's a lot. And then there's this meta type, which just tags everything with all of its spans and its code locations and everything. But it's only 150 lines. It's not terrible. There is, however, the interpreter. Where is that interpreter? Let me find it. It's going to be wherever I match on these things. So case, and then, all right. So the interpreter, are you ready? Holy moly! Look at this. Oh, it's actually in this file. So it's already in this file. So it's really just this. It's not much lines of code whatsoever. So basically, the function is we take an assertion. That's our current assertion. Because this is on the object, right? So arrow.run is not on an arrow. So we take the arrow we wish to execute from A to B. We then get an in value, which is going to be in either of throwable A, just in order to sort of catch that if we want to. And then we return this trace of B at the end. It's all wrapped in this attempt thing, just in case it blows up. We don't actually blow up, and we can actually return a special trace that says that we blew up. Right, that's that throwable that's going to then get printed out red in the stack trace and all that. So, so for the arrowf case, we just, right, because arrowf is this function from either throwable A to trace, we just call the f inside of there, and we get back this trace thing, and then runs it on the left-hand side, and then it runs it again. It matches on the result of that. If it failed, it will just return the failure, and that's in the case of like the option was none and things like this. It will, you don't ever want to go past that. It's failed, and we want to report that as this kind of prismatic failure, and we're not moving ever again. If it was if it blew up, if the left-hand side blew up, well, there's that over engineering, which is currently unnecessary, that the right-hand side might catch it. So we're returning the trace that we get back. And the trace actually it mirrors the syntax of the arrows. So traces have an and then and an or and a not. If we look at the trace syntax tree, it basically mirrors the arrows, except instead of having the arrow, it just has the result of running it, this node thing, which is like all the information of its, whether or not it succeeded, some error message, et cetera, et cetera, et cetera. It's kind of this residue of the execution, which was kind of stolen from Zio's cause type, which mirrors kind of the same shape of the Zio effects to track their potential failures. And I tried to be clever at first, but actually doing that, it was really easy. And it made it so much nicer than sort of trying to pre-interpret it into some special renderable state. Just by like keeping all of the structure and just having this sort of like, chemtrails, the chemtrails of your execution, or whatever, the actual contrails. I didn't mean to say chemtrails, but it's a joke. And I forgot what contrails was. So yeah, it mirrors the execution of this functionality, and then later on you have all the information, and you can fold over it and translate it into something that's that sort of sequential, nice series of results and possible error messages. So that's another sort of like lesson in design that I kind of learned from this, which is just like, yeah, do the nice. Make a nice little ADT that represents exactly the domain in this functional composable way that loses no information, even if it's a little awkward to work with as it is, because then you have the full freedom to reconstitute it into some simpler model afterwards, rather than sort of pre-optimizing it and trying to form it as you go. No, they'll leave it, let it build whatever structure it needs to build, and then when it's done, fold over it, reinterpret it. Okay. Anyway, so we just basically take the trace of the left-hand side and then run the right-hand side with that left value representing that it died, and that could maybe catch it. Probably not, but it could. It might just refail. That's kind of the default behavior, is to just refail unless you're a special arrow that will catch an error. We'll see the arrow constructors kind of simplify all that, so you don't generally deal with the either bit there. And then if it's succeeded, you just do the same thing. I mean, you kind of do the same thing either way. It just depends on whether it's left or right, which means I could probably like have a to either method on this. But anyway, and then and does the same thing. It just, these all methods, it just runs the left-hand side, runs the right-hand side, and then builds a trace out of it. So really all of this is just running everything. And yeah, it's just kind of a simple, kind of falls out of the structure of here. And you can see it's like mostly identical. The trace is really the residue of the arrow, because we're basically writing the same methods that were used to build the arrows, except on the traces, which just have the results inside of them instead. Which means that most of the logic is actually in the creation of these arrows, which are really just these methods. So the simple version is this just sort of make either. There's sort of, it gets increasingly complicated, but basically the default version takes some A and gets you a trace of B. So basically if this dies, then we just, we die again, and we annotate it, that the fact that we rethrew the error, kind of silly. I'm not even sure if I'm using that anymore. But yeah, there's some nicer methods. So we could take a look at the actual smart assertions that uses these. So these are the actual methods that it gets interpreted into. So here's greater than. So it needs an implicit ordering. And then we're making this arrow from A to Boolean. We're getting some A that we have an ordering for. And then we're making this, so there's this trace helper, which is basically going to take this Boolean result and then return either success or failure based on whether or not that was true or false. And then there's some error message. And I have this little like sort of error message DSL because I wanted m.was to switch between was and was not depending on whether it was negated. So we kind of have to encode this message that could potentially be flipped later on based on its eventual result. And some helpers that sort of syntax highlight things and join together this little mini error message DSL. So this was greater than this. We could look at the sort of the is some case. And this one is actually really simple, where we make an option, we make this function from option of A to A, and we just have a pattern match here. So if it was the value, we succeed with the value. Otherwise, we halt with option was none, or either was left. And this like just continues along otherwise, and it's just all sort of works. So that's kind of the tour of this. So this file is where I define all the sort of the special cases and things like that. So maybe we could look at the for all iterable. So it's not terribly complicated for what it's doing. But basically, we're getting some iterable of A, and we're returning a Boolean of A, right? So it's an arrow from iterable to Boolean. And we get this seek, right? This iterable, I guess it should be called. And then we map over it. And for each value inside of it, we run this predicate arrow, which is an arrow from A to Boolean. So it's that into Boolean, like is even, is greater than whatever. So we run it eagerly here, or not eagerly because we're inside the run loop, but we kind of recursively run it internally, or in a nested fashion at least, passing in the value because it wasn't a throwable. So we pass in the value and we run the predicate arrow on this. So then we have this list of results of running it for each side. So that's how it doesn't short circuit. It actually runs it for everything such that we can get everything. So it's like not using for all, it's actually calling arrow.run per value of the list. And then we get all the failures out, and then we check to see, we want to have a nice element versus elements. We need to have nice plurality in our error message. And then we sort of manually, you don't usually build these nodes manually, but in this case, I don't have many of these cases that have these nested results. I sort of build this trace structure manually where there's this children field. And if failures is empty, then there are no failures, no children. Otherwise, I just take all the failure children and join them together. And that's kind of what's then nested as that indented set of assertions in the final rendering. So yeah, not horribly complicated. Some error message, whether or not it failed. Yeah, that's kind of the gist of the API and the design. So it's pretty simple, and there's just a lot of these, which are mostly all pretty simple. And then the arrow thing is like you can understand it pretty quickly, and trace is basically the same thing except with some debug info it needs.
So there was a question about the ability to customize the rendering, and particularly for people who do have issues with color vision. The beauty of your expression is maybe not for everyone. So there's a question of like, would it be possible to kind of plug in a different way of rendering and say like, oh, this is great, but I want to render a different way where it works for me better.
Yeah. I mean, obviously not yet. No. I guess this first step was just to get it to work, right? But the second step would be to make it nice and customizable. And I mean, there are other sort of settings you might want to change too. Like, what if your case classes are huge and you don't want to print out a case class if it's rendered result? It will like go at least 100 megabytes of information or something. Then you can't really see your test result. So I think we need all sorts of configuration in the test runner, but that should be hopefully orthogonal to that. Definitely would recommend, if you have some specific requests, open some issues in GitHub and or just post in the Slack, and we'll open them in GitHub and sort of address them.
Definitely if you want to follow up with us, we can definitely.
Yeah, it would be great to know.
We definitely want it to work for everyone.
Yeah, absolutely. And I mean, I think, I wonder, it would be great to know the terminal rendering is so limited in what you can do, but obviously there's like underlines, faded styles. Like beyond color, there's not terribly much, but you can have like plus or minuses or warnings. I think it'll generally work. I don't know if the colors are used alone to sort of show information, but kind of just to enhance what's already there. So I don't know if you're going to lose out on something beyond, the color, but it's not also holding information. It's kind of just adding to the information, not the sole signifier. But maybe I'm wrong, because I don't believe I'm colorblind, unless there's some colors I don't know about. So I'm not sure. So definitely open to feedback there. That would be fun to make much nicer. Okay, and then there's the macro stuff. We haven't really looked at the macros. We looked at the DSL, because that's kind of where most of the interesting stuff is. But we can look at the macros real quick. Smart Assert macros. So this is, 484 lines of code. It's kind of 484 lines of code. That's actually not terrible for everything it's doing. And also, as you see here, there's this list of these AST converter things, which basically mirror those smart assertions. So less than, is even, is odd, equal to, get, greater than, et cetera, et cetera. There's this list of translations from basically, they match on some code structure, and they will rewrite them into the smart assertion arrow. They'll rewrite that arrow in the arrow syntax that you would never want to write by hand, which is, well, it's actually just calling the methods in most of the cases if they already exist here. But yeah, it's kind of that. And so for each of these, there's something else here, which let's take a look at one that we already looked at. So, as sum, right? Or I guess I called it as sum here, where it actually is sum. So I should probably make those the same. And I won't change it now. But this is basically this just a pattern matcher. It just makes a partial function, and I pre-parse your syntax into this AST, and then so it's such that I can make these converters for it, and then tell it basically this is a function from my version of the Scala AST, the subset that I care about, which is not everything. So I first pre-parse the actual Scala AST into the simplified version, which is just like nots, ands, ors, methods, functions, and then some raw AST that I don't really want to deal with in any special way. And then I can match on these. So right now I want to match on a method that's called get. And then if the left-hand side's type is a subtype of option of anything. And then I want to turn it into that is sum AST. So I'm going to call is sum on it. I'm going to rewrite .get on options to an assertion is sum. So that's kind of what all of these do. They specify what the method is going to be called. Sorry for the cat wants to be center stage. Wormy. And then rewrites them. So just a lot of these, that's most of the file, or a lot of the file is just describing all the ways to translate from the method into something else. So yes, AST converter is this thing that basically has this unapply method that will just turn it into an option of some information that I care about. Yes, including its span and all that stuff. Okay. Then I have some annoying stuff to just like get the the actual text in the file, and some other little helper methods that are the normal sort of noise that you need with macros. But the sort of the overall structure is, so here it is. Here's the important bit. We get some like, the position of the code and all that stuff. But then we parse the tree, the syntax tree that we get. That's actually the code that we wrote. We parse that into our internal ASP. This thing, the ands, the ors, the nots, the methods, and then we generate an assertion tree from that. So we go back to a Scala tree, regenerate here, and you can sort of see this is the arrow syntax. So if it was a not, we use this not function. If it's an and, we take we call it recursively on the left-hand side, and then join it with and on the right-hand side. And there's all this additional extra boilerplate for just tracking those spans such that we can highlight things in a nice way, and so on and so forth. And there are a couple special ones actually for all and for each that I just did here, or and exists that I just did here, instead of abstracting. This is really the only cases I cared about to be all special. And otherwise it will, there's this arrow from function. So if it's a generic method, we just do this one. Oh, and this matcher thing is kind of what matches all of the special ones. So it takes all of the special AST conversions, and this will handle matching on our predefined arrows. So we're getting those arrow smart assertions here. So if it matches this, we'll use like is_sum as the right-hand side. And we'll just basically end up with a big chain. So to sort of show off what we get, I'm going to just add a print method to something. So let's go to assert one-impl, which is used in, I believe, most cases. So let's print out the block. We get that print line results. Let's take out the code block, and then let's go back to our smart assertions spec and comment out most everything, and then write a really simple version. Oh yeah, okay. Let's check this out. So we had our sort of expectations here. Let's see. It's probably going to recompile. Is it already done? Yeah, it's already done. Okay. So let's take out what the for this method, what we got. Okay, looks horrible. Let's first start out just by removing all these packages, and then it really annoyingly changes greater to this. And now we can sort of flatten it a little bit, or maybe we can't flatten it a little bit, but we can kind of get an idea of what's going on. So this is the code it generated. So it's first of all, it's wrapping this assert thing, which is just a little wrapper to hide the arrow from the users. But if I have it in there, it can actually run. So we could run this instead, and it should work. So yeah, it works, and it looks the exact same as it did previously. So 1, 2, 3 was not less than 10. This is the code it generated, and basically we could see that the result, this bit, got turned into arrow.succeed. So that's the first bit. That's result, and it also got its span. So it got its position, right? 0 to 6 was kind of what result is, which allows it to print that out. And if it failed or blew up for some reason, we could highlight it exactly here. But it also allows us to sort of reconstitute via this code at the beginning what the actual string should be for that. And then we pipe this into, smart assertions is sum, smart assertions less than. We pipe this into is sum, which is what get gets turned into, right? And then it has its own span. And then we call age on. So that's this kind of generic version from function. So we translate age, the syntax tree of this, we know it's a function going from person to something. So we lift the left-hand side basically just into an argument, and then we call age on the argument instead. which will work. And if this blows up, we'll get the exact error and we have the span. And then less than 10 actually gets turned into its own thing. And then we sort of annotate it with the entire code string, and then we add the code location. And that's kind of how it works. So it's actually, you could write it like this. This would be horrible, obviously, but the nice thing about this structure is that it's really easy to rebuild it sort of in a way that you can see it's only 400 lines of code, and the actual parsing code is probably even too complicated. I didn't really try to refactor it too much. Probably be simplified, but it's pretty straightforward. It's not doing anything too clever. It's just kind of recursing from right to left, slowly translating it into these assertions, and then just arrowing them together. So they don't have to they don't have to be concerned about anything else really. It's just a nice inductive definition instead of the original version we had, which was a nightmare and really hard to extend. Yeah, so that's kind of what they are. I hope that was an interesting tour of the code. Are there any questions?
So I think we talked about the one about the rendering. There was another question about integration with other libraries that use zio-test assertions. So like Zio Prelude, where currently we're using kind of the assertions to power like validation of types, or like the some of the like smart types. So how do those fit together?
So currently, no, but we have been thinking about it, because one might imagine it might be cool to have a sort of a refined type library sort of thing, or new type library, where you just got to write Scala code like this as your assertion. Like, that's actually pretty great. A lot of the times it's just like, oh, you want this natural number thing where it can only be positive. Well, wouldn't it be nice if you could just sort of have some constructor where you just said, well, this has to be greater than 10. Obviously, this won't exactly work at all, but something like that, where it's just like, you just write Scala code and you don't have to do this weird sort of type natural equals min or whatever, greater than 0, and it's all this type level thing, which is cool that it works. But as these get more complicated, it's pretty awkward to deal with writing type level functions. Like, it's way more natural to write actual functions in Scala rather than lifting them to the type level as the refined library has you do. So it would be cool to explore doing the same thing for new types, but that is kind of just a daydream at the moment. So yeah, you might see, yeah, stay tuned.
And then there was a question about just like, how did you pick the for all and exist to be kind of clearly got like a lot of special kind of attention in rebuilding this versus like anything else in the Scala library. I think part of that was just those were kind of both existing assertions and kind of presented this problem of kind of branching out in a different way than kind of a linear way, but maybe just talk about that a bit.
Yeah, I mean, it was, yeah, I think there were some existing assertions. I don't know if the existing assertions print out the each error individually. It just kind of crossed my mind that that's something that's kind of cool and something that I use for all and exists a lot. I mean, I think it's kind of a common thing to do in tests. I'm sure there are like common cases that could be specialized equally, but I wanted to have something that would force that functionality and kind of force the design to be able to handle it in a way that didn't make everything so bad. And it's actually not too specially cased. I mean, it's using most of the same arrow stuff, and I just didn't like factor out a more extensible way because I only did 2 of them for now. But if more cases come up, they could probably be less of a special case, because it's really just in the rendering logic. Yeah, I just didn't pull out a helper constructor for doing that, but I think that could be the case, this pattern where you have nested, some kind of nested function. Yeah, it's just kind of the fun design challenge and something that I thought would be a cool thing to do.
Yeah, well, I mean, I think we're all, and I think all Zio users are very glad you did.
Woo.
Awesome.
Well, yeah. All right, is that all right? Cool.
I think that's it's a pretty full session. That's awesome.
Yeah, that was fun. I hope everyone, well, if you give this a shot and it blows up on you, or you want it to be smarter than it is in certain cases, please let me know. And happy to do that. Also happy to pair if someone wants to add some themselves and has some ideas, and happy to sort of show you how it works and and pair and do it live together. But either way, no pressure.
Awesome.
You can also just complain or yell at me. Yeah. All right.
All right. Bye, everyone.
Okay. Yeah. We're good. Bye. Until next week. Is there another chat or is it? No, thanks. Yeah. Thanks for.